All right. So today, very sad day for me personally, the end of our lectures. But we end on a bang. I like this subject in particular, this concept of large deformations. It's definitely something that introduces a significant increase in complexity to the theory, but as you'll see, it's really not such a great leap beyond what we've covered. And that's kind of why I think it makes sense to treat this as sort of a review subject. When we started out in this class, we went through chapters 1 and 2. We went through the different governing equations of mechanics, and we related all these different, quantities of interest to mechanics generally. We related things like displacement and strain, these deformation quantities that characterize the motion of bodies as they undergo the action of some external forces that might be applied to the body. And those forces themselves also had to be governed by, principles of equilibrium, that the sum of forces acting on somebody had to sum to zero for it to stay in whatever its position was, if it was under a state of static equilibrium. And we developed equations that related all those different things. We related, strain and displacement. We, postulated this description of equilibrium. And we also found a way of connecting these different variables, these motion-like quantities and these force-like quantities to one another through our constitutive law, or basically our stress-strain relationships. So all of these things connected together gave us a description of how bodies move under the action of some externally applied forces. And that, broadly speaking, was mechanics. So all of these things put together gave us, the equations of elasticity, more specifically, examining how bodies behave when we treated them as these continua and described how they might undergo some local stretching surrounding individual material points, and how we were able to achieve equilibrium, now posed as kind of like a condition of equilibrium that had to be satisfied in this pointwise sense throughout the entire body. So all these concepts connected together, and we came up with this nice theory of elasticity, but it was limited to the fact that we had assumed certain things, and more specifically, we had assumed that the deformations that were occurring were relatively small. And that was characterized, and reflected through all these equations that we developed. And last lecture, we decided, well, let's relax that assumption. Let's expand things a little bit more. And we came up with slightly more general expressions for some of these quantities. We came up with a different strain displacement relationship. We came up with a totally different description of strain, this particular quantity being the Green-Lagrangian strain tensor, which at the end of the day actually didn't look so different from the strain tensor that we had previously developed under the assumption of small strains. At the end of the day, it really only differed by this extra term that we threw in here at the end. So not so different, not just a minor tweak to go from small displacements to now potentially large deformations. So that's nice, that's satisfying. And equilibrium, actually, we decided that there were really two ways that we could express equilibrium now if finite deformations or large deformations were occurring. We could express equilibrium either, defined relative to some undeformed or reference configuration of the body before, it's actually gone through whatever motion that it, undergoes due to the applied loads. Or we could express equilibrium in the current configuration, the deformed configuration of the body. And if we did that, if we did the latter thing, it turns out that the equations of equilibrium didn't really change all that much. We had to be a little bit particular about how we define these different quantities of body forces, stresses, and in some cases, the partial derivatives of the stress as it might vary through the body, such that all those things were defined relative to the current deformed state of the body. But at the end of the day, equilibrium is equilibrium, forces are forces, and it didn't really change that much. So equilibrium, we had to maybe tighten things up a little bit, but it was the same equation at the end of the day. So we revised our compatibility relationship, our strain displacement relationship. We reaffirmed our equilibrium relationship in the case of large deformations. Now the constitutive law, the one thing that we didn't get to last time, and the thing that we'll discuss in today's lecture. How do we relate these force-like quantities, things like stresses, to these strain-like quantities, now that we've come up with a slightly different description of what strain means, and now that we've established that there's not just one type of stress, there might be different descriptions of stress depending on how you're defining, forces. Is it per unit of area in the undeformed reference configuration, or is it a force per unit of deformed area? So we had to be a little bit careful there. Now, really the question is, if we'd previously established a relationship that, and at least in the case of small deformations, looked something like this. We assumed some kind of linear relationship between strains and stresses as they might arise in the body. And this assumed linear relationship for isotropic materials had a relatively nice, simple form. It involved really only two constants or material properties that we had to define. And that could be, any two that you like. You might prefer Young's modulus and Poisson's ratio. You might like the Lemay parameter and the shear modulus, or the bulk modulus. Pick any two of those, and you can uniquely define this isotropic elastic relationship between strains and displacements. And that was valid in the case of assuming that the strains remain small, that the displacements of the overall body were small. And we came up with this unambiguous description of, what strain meant, what stress meant, and we could come up with this linear elastic relationship between those two quantities. But it might well be a question that you'll want to ask is, well, can we just take that same description of this, stress-strain relationship and generalize it directly through this kind of extension, just substituting that small strain tensor with our green Lagrangian strain tensor, and then just say, oh, well, that's our constitutive relationship. And that's the end of the story. And then that's finite deformation mechanics. Wouldn't that be nice? Wouldn't that be nice? What do you think? Do you think this is something that we could do? Just say, I don't know, let's just pick the Cauchy stress tensor. Let's say the Cauchy stress tensor is just some linear function of the green Lagrange strain tensor. Who says that's, that'll work? And who says it won't work? Yeah, some hesitancy, some like uncertainty. Well, I think it's probably no surprise. It wouldn't be really interesting. I wouldn't have built it up if it wasn't kind of like a notable question. But really, at the end of the day, the truth is that, it's possible we could come up with some linear relationship between the green Lagrange strain tensor and some other measure of stress. And eventually we'll come up with some expression that gives us the Cauchy stress in the body, which depends in some fashion on, this new strain measure that we've chosen. But it's not that simple. If only it were that simple, though. The problem is when we're dealing with these bodies that might undergo large deformations, and depending on how we've defined our strain measure, it really depends on how we've come up with this relationship. But in general, it's not true that you can just take this, green Lagrange strain measure and plug it into our classical linear elastic constitutive model as we developed in the case of small deformations. You can't just do that and say, well, there's our relationship, let's just move ahead. It turns out it's a little bit more complicated. So really the question is, and the thing that we'll pursue is, how exactly do we come up with this relationship between, strain, in this case, the green Lagrange strain, and the resulting Cauchy stress that would arise due to whatever deformations that the material experiences? So that's the thing that we need to figure out. If it's not this, then what does it look like? And I'll say that it's almost right in the sense that we can still assume that there is some linear relationship between green Lagrange strain and some other measure of stress. And in particular, I'll point to this particular, you could call it a constitutive model. It's a relatively simple idealization of linear elastic behavior where, at least in the case of this description, it looks almost like what we had previously. We can define some linear relationship through our constitutive modulus tensor. In the case of isotropic elasticity, it just looks a little bit like this. And it depends directly on this new strain measure that we've come up with, the Green-Lagrange strain. And at the end of the day, it gives us back some new stress tensor. I'll call it capital S, not to be confused with the lowercase s deviatoric stress tensor from way back when we were discussing, different components of, or decomposed representations of the stress. Capital S in this case actually refers to a particular stress measure, sometimes called the second Piola-Kirchhoff stress. And if you remember from last lecture, we distinguished that really there were these two alternative descriptions of stress depending on whether you were looking at things in the current configuration or the initial configuration. And the current configuration, it was the Cauchy stress. That was a description of force per unit of area over some chunk of area defined in the deformed configuration of the body. And the first Piola-Kirchhoff stress was yet another stress tensor, represented with a capital P, that was nominally force per unit of area in the undeformed configuration. But now I'm telling you, that's not it. It's not just Cauchy stress. It's not just first Piola-Kirchhoff stress. There's another one of these things, a second Piola-Kirchhoff stress. And it turns out that, we define it in this way such that, it's related to the Green-Lagrange strain through this nice linear relationship. And exactly in analog to our classical linear elastic small deformation constitutive relationship. So that's very nice. We can take all the usual things that we like, and if we've characterized the behavior of the material, measuring its different properties, like Young's modulus and Poisson's ratio, or bulk modulus and shear modulus, then we can just take those properties, plug them into this relationship, and instead, define the relationship between stress and strain as this. But being careful to say that really it's not just any stress and strain, it's the Green-Lagrange strain and the second Piola-Kirchhoff stress that are related through these kind of linear relationships. So a good question is, well, what the heck is this second Piola-Kirchhoff stress? I've said nothing up to now except for this. I've said, well, I have this second Piola-Kirchhoff stress. It's linear related to the Green-Lagrange strain, but what's its physical interpretation exactly? I mean, like I said a moment ago, we knew kind of what this Cauchy stress thing was. It was the stress that you would see in some deformed state of the body. And it had a nice interpretation and connection to tractions acting on any kind of arbitrary surface through, Cauchy's stress theorem. And that gave us a nice physical intuition and interpretation of what stress meant. But what exactly is the physical interpretation, if any, of this second Piola-Kirchhoff stress tensor? And more specifically, how do we relate it to the Cauchy stress tensor? Is there some way that we can transform our relationship for, Green-Lagrange strain to second Piola-Kirchhoff stress, yet further so that we can finally obtain some expression for the Cauchy stress in terms of the Green-Lagrange strain? That's the thing that we're going to have to spend a little bit of time thinking about. But really, there's no immediate intuition behind, well, what exactly is this thing? Well, what configuration of the body does this kind of connect to? And what kind of interpretation of force per unit of area can we ascribe to this particular measure of stress? Unfortunately, there really isn't a great physical intuition behind the second Piola-Kirchhoff stress. There are a few kind of somewhat excessively mathematical, if you can believe that I would say excessively mathematical, but it's a little bit fictitious. There's really not a great, actual physical meaning behind it. Nonetheless, we can move forward and say there is a way, in fact, to come up with this relationship that is nonetheless consistent with all the rules of mechanics that we've come up with up to this point, but it requires a little bit of a detour. It requires that we kind of take a step back and actually think about not direct relationships between, strain and displacement, but instead to think of things in terms of rate of work that we do on some chunk of material. And you'll see exactly how this all connects together. But let's actually proceed along this line of reasoning by supposing that we had some chunk of material, maybe it's a small cube of material that we've extracted from some larger body, and we can look at on the faces of this cube of material, what are the stresses that act on the exterior faces of this cube, and also what are the body forces that might act on the interior volume of this cube. So just as we did when we were looking at definitions for equilibrium, considering a similar small cube of material and all the different types of forces or exterior tractions and body forces that might act on that cube, we could look at that description of all these different forces in one of these two different perspectives, defining things all with respect to some undeformed configuration of this cube or with respect to its deformed configuration over on the right. So now that we have some conception of this cube of material, it's got a bunch of forces that act on it. After we've applied these forces, and maybe as we're actually ramping up the application of these forces, we might notice that these different cubes of material will start to deform a little bit. You know, maybe as we increase whatever external tractions that are applied to this particular cube, maybe we're stretching it out in a particular direction. In doing so, we'll notice that the cube is itself, deforming. It's also undergoing some kind of external displacements. And in the process of deforming it, we are doing work on the material. By applying these external forces, we are basically doing work and putting work into the material and storing it internally as elastic strain energy. So as we do work on this piece of material, effectively what we're doing is we're, applying some external traction, let's say, to some top face of this cube. And as that top face might be kind of like displacing upward due to whatever applied forces we're putting on that surface, they are also effectively doing work. So if you can think of the unit of force that acts on, let's say, the top face of this block of material, the force that we would be applying as an external force to this body is proportional to this traction that we're applying to the top face multiplied by, the overall area over which that kind of traction acts. And the rate of work that we're doing as we're kind of deforming that top face of this cube upward is proportional to this net force applied to the top face multiplied by, or, a dot product with the actual rate of displacement as we're kind of displacing this top face upward. So if you remember the definition of work, mechanical work is basically force times displacement, right? The overall amount of force that we're applying to something to move it some finite distance, let's call it delta U or something like that. In some sense, that's characteristic of the amount of work that we're putting into the material. So we can characterize work as this kind of net force, let's say, net external force we're applying over a top surface multiplied by the distance by which that top surface is displacing. Now, we can measure that in terms of the overall amount of displacement that that surface experiences as we kind of displace it by a finite amount, or we can express it in terms of the rate of work that we're doing by considering not a finite displacement of this top surface, but supposing that maybe we're deforming it and it's undergoing some kind of, actual time rate of displacement. So rather than supposing it displaces by a finite amount, maybe we say it's actually moving upward at some velocity. So kind of like a rate of displacement. And we can represent that just by taking, let's say, some displacement u and then putting a dot over the top of it to denote a time derivative. So u dot also, you could call it a velocity, or the velocity vector is kind of the rate at which this kind of top surface is, moving in any given direction. And it could be displacing up, it could be displacing in some other direction, depending on how we're applying the loads and everything. But the rate of work done through this kind of, velocity multiplied by whatever kind of external forces we're applying is going to give us exactly this expression. Basically, the rate of work, which I'll call W dot, It's, the time rate of work that we're putting into the material is equal to the sum of all the external tractions over the entire boundary of this cube, taken as a dot product with the, velocity of this exterior boundary. So you can kind of think different locations on the boundary of this cube might be displacing in different directions, and that might be in alignment with, or maybe not in alignment with, whatever external tractions that we're applying on this, whole boundary, and it could be variable. And similarly, if we're applying a body force over the interior of one of these cubes, that body force will also be doing some work on the material, which is proportional to this body force multiplied by also that same velocity. So maybe the velocity is, of different points is, causing it to move in different directions. In some cases, it might be moving in a direction that's aligned with that kind of body force applied to, these different points. Maybe it's not, but we can characterize the alignment between these kind of like applied forces and the motion of individual material points, again, through these kind of dot product relationships. And summing up all the external forces applied to the boundary of this cube, summing up all the kind of contributions to the rate of work from the body forces, integrating over the entire interior volume of this cube, we can come up with the overall amount of work that we're kind of putting into this system, given all of these different external force contributions. We could express this with respect to the undeformed configuration of this cube, in which case all these kind of traction-like quantities and body force terms are expressed as force per unit of initial undeformed area and body force per unit of initial undeformed volume. Or we could define this same concept all with respect to the current configuration, in which case we would just plug in different interpretations of traction, different interpretations of body force as being per unit of, deformed area or volume, and then integrating over corresponding units of, current or deformed area or volume. All right, so all of this gives us the total work we're putting into this chunk of material. And I won't bore you with the details of the derivation. If you like, you can kind of step through and take a look at some of these steps. But really, the conclusion that we reach in looking at these expressions for external work that we're doing on this cube of material, you can go through a sequence of replacements. You can notice that really traction is related to whatever the stress is that's acting on this cube through Cauchy's stress theorem. So we can replace traction by, the stress tensor dot product with whatever kind of surface normal that it's acting over. We can also take things one step further and actually, if we assume that this cube of material is small enough, then it actually does to, take everything inside of this volume integral and transform these integrals over the boundary of this domain into equivalent integrals over the interior volume, but it looks a little bit different. It involves not a dot product of, the stress tensor with some kind of exterior normal vector, but instead through basically something called the divergence theorem, something that we used early on in the class actually to derive the equations of equilibrium to begin with. But this divergence theorem basically transforms that dot product with a normal when integrated over some exterior area into a corresponding gradient of this whole thing, when integrated over the volume. So that's the divergence theorem, a transformation between area integrals and equivalent volume integrals. And then we could notice through a few manipulations and extra things that we could actually find that what pops out of this kind of interior volume integral is, in fact, one of our equilibrium equations, which we know has to be satisfied everywhere in the body. So this whole thing has to be equal to 0. And at the end of the day, what we get out of this is that this original expression for the total rate of work that we're doing on the material involving external tractions and whatever body forces are being applied is actually equivalently represented in terms of this thing, an integral over this interior small volume of material involving the stress tensor multiplied in this kind of inner product sense through a tensor contraction operation with this time rate of the deformation gradient, which, if you like, is equivalent to basically the spatial gradient of the velocity vector. So it's sort of an interesting transformation. We've gone from a description of the rate of external work that we might do on some chunk of material, and we've transformed it into a quantity that basically involves the stress tensor and the time rate of some measure of deformation. If you were to go through that same derivation, but apply everything to the current or deformed configuration of the material, you'd get a similar looking expression. It would involve not the first Piola-Kirchhoff stress, as I'm showing here, but it would involve the Cauchy stress. It would be not an integral over the initial unit of volume of some chunk of material, but the actual deformed volume of that chunk of material. And it wouldn't involve the time rate of the deformation gradient. It would involve this thing which I'm denoting by L, sometimes called the velocity gradient. It's basically the spatial gradient of the velocity vector, but where that gradient is expressed as a partial derivative with respect to the current deformed coordinates of the body. So that's a very small distinction. You can relate it actually directly to the time rate of the deformation gradient through this relationship L equals F dot times F inverse. Kind of a nice relationship. All right, so we've come up with this equivalent expression for the external work done by all these forces that we might apply to some block of material, and that's equivalent to this integral of this inner product term. And in fact, this term, this inner product of some stress measure and some deformation measure, is in general referred to as the stress power. It's the rate of work done by taking some small unit of material and subjecting it to some kind of time rate of deformation as measured through one of these deformation tensors, either the velocity gradient or the deformation gradient, its time rate. So all those things seem like a kind of an unnecessary digression. Where exactly is this leading, right? Well, how is this useful to us in terms of how do we come up with, again, that relationship between second Piola-Kirchhoff stress and Cauchy stress? That was the thing that we wanted. So how do we get there? Well, you'll see in a moment, but really we need to also define one other kind of energetic quantity. And in fact, we've already defined it. It's this notion of internal or elastic strain energy. Remember what that was. We defined strain energy in some chunk of material as basically being proportional to the integral over some, let's say, discrete volume of some strain energy density function. So strain energy per unit of volume that's proportional to the amount of strain or deformation that that unit of material has experienced. And we could compute what exactly that strain energy was by, let's say, in the uniaxial case of some chunk of material that's undergoing only uniaxial strain and only uniaxial stress, or basically maybe only uniaxial stress, let's say. It could be straining in other ways. But suppose we had that, we could compute this elastic strain energy as really just the area under this uniaxial stress strain curve. So if we happen to express, axial strain, let's say EXX, the Green-Lagrange strain in the XX direction, versus the second Piola-Kirchhoff stress in the XX direction, we know, according to this linear elastic or assumed linear elastic relationship between Green-Lagrange strain and second Piola-Kirchhoff stress, that this should be indeed a linear relationship. And if we're using that kind of St. Venant-Kirchhoff type of model, the generalization of our nice linear elastic model in the case of small deformations, then we can assume that the slope of this diagram should be basically just proportional to, let's say, E, or the Young's modulus of the material. It gets a little funny because, now we're duplicating all these, terms. E could mean Green-Lagrange strain, or it could mean this material property. Hopefully things are clear nonetheless here. But the idea is we can compute the elastic strain energy just by taking the integral of the stress with respect to the strain. So whatever this area is, we can just, compute it. And, what is area other than, the integral under some curve? So if we have some representation for stress, which depends on strain, we can take the integral of stress with respect to strain and then come up with the area under that curve. So in the generalized setting, rather than just, having a one-dimensional stress-strain kind of relationship, we might have a bunch of different components of strain and a bunch of different components of stress. And the generalized expression for elastic strain energy was really just this tensor contraction or inner product between stress and strain, represented as tensors, and integrated from a state of zero strain up to whatever current or applied strain we have in the material. And quite simply, it boils down to something that just looks like this. 1/2 the inner product or tensor contraction of the stress tensor and the Green-Lagrange strain tensor. So that was elastic strain energy. Now, how does this help us? Well, consider for a moment that if we have this expression for elastic strain energy, and if we remember exactly how we defined our constitutive model through this assumed linear elastic relationship between Green-Lagrange strain and this second Piola-Kirchhoff stress, we could plug everything in and we could represent this internal elastic strain energy thing just directly as a function of the Green-Lagrange strain. So, just forgetting about the fact that there's this thing called stress. We just say that strain energy depends only on strain. And we could express this kind of scalar term in that sense. So plugging it in, we can get something that looks kind of like this. And maybe it involves, different properties of this Green-Lagrange strain tensor, maybe, E times itself, and then take the trace of that thing, basically the sum of the diagonal entries of E times itself, multiplied by the shear modulus plus 1/2 of the, Lemay parameter times the trace of E, the sum of the diagonal entries of the strain tensor, and then that thing squared. And at the end of the day, what's interesting is that if we look at this relationship, we actually notice because of the way that we've defined this expression for elastic strain energy, it's 1/2 S times E. If we happen to try to take the partial derivative of this thing, which itself was an integral with respect to strain, if we take the derivative of this thing with respect to strain, it's kind of like we're canceling out this integral operation. So if we did this kind of integral over some variation of strain to get the definition for elastic strain energy, equivalently, we could go the reverse direction and take the derivative of the strain energy with respect to the different components of strain in order to come up with what are these components of stress. And that's precisely how these things called hyperelastic constitutive models determine expressions for the strain, or rather for the stress. It's not necessarily by supposing that there is some relationship that links strain and stress in this nice fashion. They actually typically start from here. They postulate what the strain energy looks like, expressed exclusively in terms of whatever strain measure you prefer. And in fact, it doesn't really matter which strain measure you choose, as long as it's some valid type of strain measure that applies in the case of finite strains. You can just come up with some expression that says this is the internal strain energy in this piece of material. It depends in some fashion on this kind of particularly chosen strain measure. And then if I wanted to know what's the stress and how does it relate to this particular strain measure, all I have to do is take this expression and take its partial derivatives with respect to the individual components of that strain measure. And what I'll get back are the individual components of the corresponding stress tensor that is related to this particular strain measure. So that's really how you define stress in this somewhat more general setting where you have large deformations occurring. So we came up with this definition of stress a priori. We kind of said, well, wouldn't it be nice if we could find that? And the way that people go about doing that is usually they don't just say, well, let's just move ahead with this. They actually say, well, let's figure out what is the definition of the strain energy that would give me this. And then the stress is simply defined through these partial derivatives. So that's really the key distinction. All hyperelastic material models go about defining, some potential energy or internal strain energy, and then define stress as kind of its partial derivatives with respect to the strain. So that's a little bit of a departure from maybe what you're comfortable with, but really, it's really no different from what we've talked about up to this point. That, if you define strain energy in this consistent way as it's kind of like an integral of stress times strain, then taking the derivative of strain energy just gives me back the stress. So it shouldn't be so bad at the end of the day. And in fact, this is actually closely related to a concept that maybe you learned about in your could be mechanics of materials class. It might have even been in your structural analysis class, but this idea of posing some form for potential energy or internal elastic strain energy and taking its derivatives with respect to some displacement-like quantity to get some resulting force-like quantity, that this concept is actually closely linked to something called Castigliano's theorem. If you remember that, or if you ever heard of that, basically it's exactly this same principle, just applied in this particular setting of coming up with a particular force-like quantity as the derivative of some potential energy function. So that's very nice. It's kind of a nice starting point for how we go about devising a bunch of different types of material models, not just ones that look like this, but there's many different ways that you could choose to just pick a different representation of how you're going to represent internal elastic strain energy. And then you come up with different descriptions of stress that drop out of that. But now that we have this expression for this internal elastic strain energy, now we want to come and connect it back to this external rate of work that we were doing on the material. If we were deforming some chunk of material under some externally applied forces, and we found that the rate of work done by those external forces was directly equal to the integral of the stress power thing. Now, what if we said, whatever external work we're doing on the body, it can't just, go nowhere. It has to go somewhere. And there's really only two options for whatever work we're putting into the material, there's only two options for where it can go. It can either go into elastic strain energy, so energy that is stored in the material when I stretch it out. And that is basically represented by whatever goes into the internal strain energy as measured through the integral of this kind of elastic strain energy in the body. So if, let's say, I'm putting in work, the rate of work is positive, and let's say the rate at which the internal elastic strain energy is also positive, then basically it means that I'm putting in work, and at the same time, it's getting stored as internal elastic strain energy. So both of those things, at least when I'm doing positive work on the material, you would expect the strain energy to be going up because some of that should be going into this stored elastic strain energy. But it's not necessarily the case that all of that energy is going to be stored as elastic energy. Some of it might be dissipated. It could be due to viscous dissipation effects. It could be due to plasticity. So in general, you might be doing more work on the material than the material is actually taking up and storing as elastic energy. And in general, that's expressed through this relationship. It says that I might be doing more work than the internal elastic energy might be able to take up. And whatever excess work that I'm putting into the material that's not balanced by the increase in internal elastic strain energy is basically just lost. It's dissipated as heat or through permanent configuration changes like plasticity in the material. And as long as I satisfy this relationship, I end up satisfying the second law of thermodynamics, which basically says that I can do work on the material. I can permanently deform it, but there's no way for somehow the material to spontaneously give me back some excess energy out of nowhere. So reverse whatever plasticity occurred and then convert it back into mechanical energy. That's just not physically possible. So in general, dissipation always has to be positive. There's no way for energy to be generated out of disorder. But in general, we can represent all these different relationships by noting that, again, if let's say we have the stress power term, the rate of external work we're doing on the body, and we have the rate at which internal elastic strain energy is increasing, we can express this as something represented over some unit of volume, or we can express it in kind of like this per unit of volume sense. So a dissipation rate per unit of volume, which is basically an expression of the stress power minus the rate of increase in the internal elastic strain energy density. And again, that thing also has to be strictly positive or zero. But in the special case where, as we like in elasticity, if we know that there's no dissipation going on, or approximately no dissipation, such that any work we put into the material we expect to get back, we expect that we can recover it through mechanical work, such that that process is entirely thermodynamically reversible, then it suffices to say that really the dissipation, there's no energy dissipation going on. So we can say that the rate of energy lost through mechanical work is just equal to zero. Any external work we're doing through stress power applied to the material has to go into elastic energy that's stored in the material. And those two things then have to be, the same. They have to cancel each other out. So in other words, we come up with this relationship that the stress power is just directly equal to the rate of increase in elastic strain energy. And because of how we've formulated our expression for this internal elastic strain energy, in terms of, again, this description of stress times, some rate of applied strain. It's kind of the integrand of that integral that we were carrying out previously when we were computing the total elastic strain energy. It was the integral of stress times, some increments of strain taken over many different steps. But if we now take the time rate of that thing, we get back our description of stress times this strain rate like thing. So really there's an equivalence between this rate of external work and this rate of internal work that goes into the material. And if we remember our particular description of this Green-Lagrange strain tensor as being expressible in terms of the deformation gradient itself, and we take its time derivative, we take its time rate, we come up with some equivalent expression that involves the deformation gradient and its time rate. We can plug it into this thing, and at the end of the day, we'll get a slightly different expression, but one which allows us to make an interesting observation, that these two things look almost identical. And in general, if we don't really know, or if we don't really care about that what exactly is the time rate of this thing, it could be arbitrary. We don't really know, and we don't need to be specific about what specific time rate of this deformation gradient is occurring. If it's arbitrary, then really the only way for this expression to be satisfied all the time, regardless of what kind of the rate of the deformation gradient is to have these two things be equal to each other. Or in other words, we find at the end of the day, as a consequence of this argument of stress power equivalence between rate of external work and rate of increase in internal elastic strain energy, for that to be satisfied, we have to have this relationship between, in this case, the first Piola-Kirchhoff stress and, on the right-hand side, the deformation gradient multiplied by this particular stress tensor thing that we've come up with, the second Piola-Kirchhoff stress. So at the end of the day, we find this rather nice, succinct relationship between first and second Piola-Kirchhoff stresses. And obviously, we can take that one step further. We can say, now that we know the relationship between first and second Piola-Kirchhoff stress, we can remember from the previous lecture what our relationship was between first Piola-Kirchhoff stress and Cauchy stress was, and rearrange things a little bit more. At the end of the day, we'll get an expression for the Cauchy stress in terms of this second Piola-Kirchhoff stress. So we did it. It required a little bit of a digression. It required thinking about things and almost diving into thermodynamic principles in order to come up with this expression, but it's fully consistent. It's, energetically consistent with, sometimes called thermodynamically consistent. It's a consistent representation of how those two different measures of stress should be related to one another. And, it involves also, I'll just define here for convenience, J, which is really just nothing more than the determinant of the deformation gradient. Oftentimes you'll see that that's a commonly used symbol, but in any case, it's just second Piola-Kirchhoff stress, left and right multiplied by F and F transpose. And what's interesting about this expression is, certainly we know that the Cauchy stress has to be symmetric. That was a requirement in order for moment equilibrium to be satisfied. it turns out that the second Pula-Kirchhoff stress is also symmetric. And you can kind of see that just by virtue of how this relationship unfolds. If we're left and right multiplying by the same tensor, just F and F transpose on the left and right, then the resulting matrix that comes out of this matrix multiplication in sequence gives us, back a symmetric tensor. So both of those two measures of stress are symmetric, which is kind of nice. It's convenient. But at the end of the day, that finally comes together. All of our different expressions for the governing equations of mechanics, now in the presence of finite deformations, are complete. We've figured out our revised strain displacement relationship in terms of this Green-Lagrange strain measure. We've come up with our new constitutive law that involves, again, some description of a second Pula-Kirchhoff stress that's derived directly from some postulated internal strain energy function that might depend on the Green-Lagrange strain measure. We have a way of transforming that particular second Pula-Kirchhoff stress measure into an equivalent Cauchy measure of stress. And finally, we have equilibrium, which is expressed directly in terms of, in this case, the Cauchy stress, as defined relative to the deformed configuration of the body. So it all came together. And then in the end, it doesn't really look all that much more complicated than what we had derived previously. It didn't really change too much. So really, what is the consequence of doing all this? And why do we care about large deformations in general? Well, here's one relatively simple example that I'll point to. The case of some uniaxial bar or some uniaxial chunk of material. Maybe it has initial unit size, or maybe each individual kind of leg of this cube has length delta x, y, and z. And let's imagine that we put this cube of material in a state of uniaxial stress. So we apply some uniform force F on both of the x faces of this cube. We stretch it out in some direction such that, maybe it elongates in one direction and then it contracts in the other two directions. And we want to know, given these more general expressions that relate finite deformation measures of strain and stress all together and equilibrium, how exactly does our classical description of linear elasticity connect and compare with now descriptions of finite strain elasticity? And we'll look at this from the perspective of the different deformation quantities of interest first. So imagine we had this cube. Originally, maybe it's a cube, and then after deformation, it stretches out in one of these different dimensions. We can measure the deformation gradient, capital F, as basically characterizing the stretch or the deformation experienced by each one of these three different edges of this cube. After deformation, the stretch experienced by, let's say, the X kind of edge of this cube is going to be proportional to effectively the ratio of the final deformed edge of that cube divided by the initial length or edge of that cube. And we can measure that kind of stretch ratio for each of these three different edges of this cube. So lambda x, the stretch ratio associated with like this edge of the cube, is certainly going to elongate. It's going to get bigger. And then lambda y and lambda z, the stretch ratio associated with these y and z directed edges, is probably going to be less than 1. It's going to shrink a little bit. We can characterize then the resulting deformation gradient rather conveniently as just a 3x3 matrix with only diagonal entries, zeros on the off diagonal, and on the diagonal, we have just the stretch ratios of these three different things placed there. So rather hopefully intuitive description of now deformation gradient in this context expressed in this simplified format. And we can also take this one step further. I said we liked having this deformation gradient. It told us how individual line segments deformed before and after deformation, but we could make a few manipulations and come up with slightly different descriptions of deformation that don't just map how individual line segments deform, but we can come up with some expression that tells us how individual kind of planar area segments deform, or how different volume units deform under this applied motion. So in the case of small units of area, the relationship was expressed in terms of this cofactor of the deformation gradient, which was the determinant of the deformation gradient times its inverse transpose. It turns out that really in this simple example, on the diagonal, this cofactor thing actually just has the pairwise products of each of these stretch ratios just paired together. So in the XX entry of this cofactor term, it's actually a lambda y times lambda z, kind of counterintuitively. So basically what that means is if I have, let's say, some kind of unit of area, let's call it capital A, associated with this front face of the cube, or a face of the cube whose normal is in facing the x direction. After deformation, that unit of area, capital A, is going to shrink a little bit. It's going to, deform into this smaller area, denoted by lowercase a. It'll still maintain the same normal orientation. So the normal to this plane was originally aligned with the x direction, and that's still true after deformation. But if we want to measure the relative change in area of this small patch of kind of surface area, really it should be self-evident that to determine that, all we really have to do is take this original area and then actually multiply it by both lambda y and lambda z. And you can see that through any transformation that you would apply to, some vector whose orientation is described by the surface normal and whose area is described by, let's say, delta y and delta z multiplied by each other. And then on the left-hand side, what we'll get out is the same vector, same orientation, just scaled differently, telling us that its area may have shrunk. And in fact, it'll have shrunk proportional to lambda y times lambda z. Okay, so we have now a way of describing how this small chunk of area, lowercase a, will have shrunk under this description of deformation. And that's particularly relevant when we wanted to describe different measures of stress. So to remind you, we had two ways of describing stress. Force per unit of initial undeformed area, or F divided by capital A, or force per unit of deformed area, F divided by lowercase a. And really these two things, are linked to one another precisely through that relationship that we just showed. So lowercase a is really just lambda y times lambda z times uppercase a. In either case, we could describe stress in one of these two different ways, and they look almost the same. If we're assuming it's in a uniaxial state of stress, then the only component of stress is axial stress in the xx direction. The only difference here is the scaling. The first Pula-Kirchhoff stress, or the engineering stress, if you prefer, is, again, the force per unit of initial area, whereas Cauchy stress is force per unit of current area. If you prefer, you can call this the true stress. All right, so all of that being equal, given our descriptions of either first Pula-Kirchhoff stress or engineering stress, alternatively, if we prefer, we can express everything in terms of Cauchy stress or true stress. We can use those relationships we just derived to transform this representation of stress into a representation for the second Pula-Kirchhoff stress, the thing that we had a relationship for that gave us a way of relating stresses and strains, in particular the Green-Lagrange strain. But before we did that, before we can apply our constitutive relationships, we actually had to take whatever these different measures of stress are and transform them into this particular stress measure. That's kind of the extra step that we have to do when we solve these types of large deformation problems. So at the end of the day, for this problem, it's not so bad. If we wanted to find, let's say, second Pula-Kirchhoff stress, given first Pula-Kirchhoff stress, all we have to do is left multiply by the inverse transpose of the deformation gradient, which is equivalent to just dividing all these entries by, the diagonal entries of the deformation gradient. So if before we just had F divided by A, now it's F divided by A times lambda x, the actual axial stretching in the axial direction, which seems a little unphysical. What the heck is this? Again, like I said before, second Pula-Kirchhoff stress doesn't really have a great physical intuition behind it. It's really just a convenience for how we relate stresses and strains. But in any case, we have it now. We have some measure of the SXX stress, the second Pula-Kirchhoff stress, expressed in terms of whatever external applied force and whatever axial stretching might occur in the X direction for this cube. Now we can go through our constitutive relationship. Now we can say, I know that the state of stress in this cube under a state of equilibrium is going to look something like this. And to make things simple, I'll say that all of the shear stresses in this cube are zero, assuming that it's not going to get skewed or anything. So really, there should only be normal stresses acting on this cube. There might be, obviously, some normal stress in the X direction, on this X-directed face of the cube, and on these lateral surfaces, whose normals might be in the Y or Z directions, we assume that there's no stresses there. So we can just say that SYY and SZZ that would otherwise be in these two slots here, that those are just zero. So at the end of the day, we just have SXX and SYY and SZZ are zero. Then we can just go backwards. We can say, invert our constitutive relationship. We can express it rather conveniently just in terms of Young's modulus and Poisson's ratio through this kind of matrix vector arrangement, or we can express it as individual relationships. We can then come up with the explicit expressions for the different longitudinal components of strain. But these expressions for the strain are, remember, expressed as the Green-Lagrange strain tensor components. It's longitudinal components. Nonetheless, everything else looks the same. Everything looks the same compared to our classical linear elastic relationships. The only difference is we have to be careful about which particular measures of stress and strain are we looking at. So at the end of the day, we'll get some expression for longitudinal X strain, which is going to be proportional to just SXX divided by Young's modulus. And then obviously we can come up with expressions for the longitudinal strains in the transverse directions, and those will just be proportional to this kind of negative of that EXX multiplied by the Poisson's ratio, or the amount of contraction that should occur. Okay, so all of that put together, we now know that our Green-Lagrange strain tensor should look something like this. It'll have those different longitudinal components of strain organized in this kind of 3x3 array and just this diagonal format. But we want to relate it back to our original description for the deformation gradient. We kind of presumed that the deformation gradient should kind of look like a diagonal tensor also, whose diagonal entries are just these three stretch ratios along the diagonal. And if we know that, then we can come up with a relationship between these individual components, EXX, EYY, and EZZ, and those corresponding ratios of stretch. Through this definition, it turns out that that's rather simple. Any one of these diagonal entries is just 1/2 the square of one of those stretch ratios minus 1. So that's true for all three of these different components of Green-Lagrange strain. We come up with then these different expressions and relationships that link the axial SXX second Pula-Kirchhoff stress to these different components of stretch ratio in the X, Y, and Z directions. And we can simplify things further. We note that really the stretch ratio in the Y and Z directions from these two previous expressions, that they should actually end up being the same. This thing and this thing are the same thing. Or in other words, epsilon YY equals epsilon ZZ, which means that lambda Y and lambda Z, those two things should be the same. And same thing here, we can come up with some direct expression for lambda X expressed in terms of SXX. So at the end of the day, we get a slightly simplified point of view here. We've actually come up with a relationship between stretch ratio, or kind of like the amount by which each of these different edges of this cube are elongating, and we related it to the applied stress, the second Pula-Kirchhoff stress, in the axial direction. The only thing that we have to do now is remember how we defined second Pula-Kirchhoff stress. It was total applied force divided by initial area, and then to do that extra transformation, we had to divide by the axial stretch ratio. We can plug that into these relationships and move things around slightly until eventually what we get is this. We come up with some expression or relationship between whatever axial or applied force we put on this cube, and we can relate it back to the amount of axial stretch that occurs in this cube. And given that information, we can also come back and figure out how much do the lateral faces of this cube contract inward once we figure out what this kind of axial stretch is for whatever applied external force we might apply to this cube. We can also figure out different expressions for different measures of stress, like the Cauchy stress or the true stress that would be applied over this kind of front face of the cube. And really all that it requires is, again, if we have this expression for force, we can plug it into our expression for Cauchy stress, which is really just the initial area scaled by these different edge scaling ratios, where the lambdas and the y and z direction should be less than 1, indicating that this overall area is actually shrinking. And if they're less than 1, what this basically means is that, f divided by a now divided by some quantity that's less than 1 implies that actually sigma xx is going to be greater than, f divided by a alone. So as the cross-sectional area starts to shrink, the Cauchy stress is actually going to appear to increase, and inversely proportional to the rate of decrease of the cross-sectional area under deformation. Now, what's interesting is that we can compare all of these different measures of stress as we've previously developed. We can look at Cauchy stress, that force per unit of deformed or final area, expressed exclusively in terms of this axial stretch ratio. We can also look at engineering stress, nominally defined in terms of these finite strain and stress measures, and it'll look almost the same. It just won't be divided by this extra term. So almost the same. And then finally, we can compare it against our classical linear elastic theory. What would the stress be if we just assumed linear elastic deformations? So in other words, that's kind of equivalent to saying that the axial stress should just be equal to Young's modulus times lambda minus 1, which if we note, we can define this lambda, the axial stretch, as basically just being, if you like, the initial length plus the change in length, ux, divided by the initial length, or just 1 plus ux divided by delta x. If you like ux divided by delta x, that's just the axial small strain, which if we plug it in here, gives us back what we expect. That axial strain or axial stress in the small strain setting is just equal to E times epsilon xx, the small strain in the axial direction. So it all boils down to the same thing that we expect at the end of the day in the case of small deformations. But what if the deformations aren't small? And what is the consequence of that for this particular problem? Well, if we were to plot these 3 different things as a function of this axial stretch ratio, when the stretch ratio is equal to 1, which basically says that the cube hasn't deformed at all yet. We're just kind of starting out with an initial cube, and then maybe we start ramping up the applied force, such that now, this axial stretch ratio is increasing, or the amount of axial strain is increasing as we kind of move in the right-hand direction. All of these 3 different measures of stress close to this axial stretch ratio being equal to 1 will look basically the same. They all pass through the same point, and they all have basically the same slope at this point, which tells us that as long as the amount of strain that we're putting into this material is relatively small, it doesn't matter. It doesn't really matter whether you're considering finite deformations or small deformations. It doesn't matter. They all boil down to the same thing, which gives us confidence in affirming that our classical theory of elasticity still works. It's still valid so long as the deformations are small. But what happens is we increase the amount of deformation. And in particular, if we increase the deformation more and more and more, we'll notice, according to our linear elastic relationship between axial strain and axial stress, that assumption will basically look like a straight line. The small strain and small stress relationship is just going to look like a linearly increasing function. And it doesn't matter how big you make that strain, you could take it forever. And the stress is just going to continue to increase linearly indefinitely. Now, what about the engineering stress, or the second Pule, or the first Pule-Kirchhoff stress? Force per unit of initial undeformed area. Well, it'll actually increase at a faster rate than this other kind of assumed small deformation measure of stress, but it won't get crazy. And largely that has to do with the fact that, the area over which this force is acting is assumed to be the same. It's the undeformed area. So we linearly increase the applied force, and at least from this perspective, it doesn't look like the stress is getting very big. But the reality is, as this kind of cross-sectional area shrinks, the area over which the same force must act in order to be in a state of equilibrium, in terms of this definition of Cauchy stress, force per unit of deformed area, things will get crazy. And in particular, the apparent stress in the material, as measured through this Cauchy stress measure, is going to just like ramp off to infinity once you get to a point where this denominator in this expression is equal to 0. So there's a particular stretch ratio, or a particular corresponding, Poisson's ratio of the material, at which this whole thing in the lower portion of this, denominator will just go to 0. And at that point, this thing will blow up. So really, physically, what that means is you could have a piece of material, you could tug on it, more and more, and continue to ramp up the applied force. But at a critical point, you'll actually get to this situation where like any additional force that you apply is actually going to cause this thing to just like go under some kind of tensile instability. And that's kind of characteristic of necking phenomenon as they might occur in some kind of like relatively flexible materials or elastoplastic materials. So really, it doesn't do to always assume small deformations, particularly in those settings where you have large deformations. Okay, so that's all very nice and interesting. Unfortunately, that's the last thing that I'll have to say about that, and rather anything for this whole semester. Thank you for your attention. And yeah, any questions? Otherwise, I'll see you after the break on Tuesday. Yeah. Oh, yes, of course. Yes, I will certainly upload a practice final. It should be representative, as was the practice midterm, of what should actually be on the real final. So thank you for the reminder, though. Yeah. Yes, I'll try to do both. Yeah. All right.